Hello everyone, and welcome to this video titled Approximating Areas. So in this video, I'll be taking you through a preview version of a Knewton Alta assignment that is also titled Approximating Areas. So please understand that this is a preview version that I'm going to be going over. So the questions I go through in this video may not be the exact same questions that you see when you work on the assignment yourself. But the objectives should be the same, and the methods used to solve problems should also be similar. So hopefully, it'll help you get through the assignment when you do it yourself. Okay, so this is what it would look like. Here we are at the Knewton Alta page. And this is a preview of what is, section 5.1. And the number might be different for you in whatever class you're looking at, but this is called Approximating Areas. You should see in the upper right-hand corner a mastery bar, right, that shows you how far along you've gotten in the assignment. Next to that, an activity log, which shows you all of the objectives. So this particular assignment has 6 objectives with 2 headings. So I'll be in the heading sigma notation for the first several problems, and then once I'm done with these 2, it'll move me up into the approximating area objectives. Then on your main page, you should see a current objective. Beneath that, a question related to that objective. And at the bottom of every question, you should see or be able to find a feedback option. So if you see anything wrong with the question or the answer explanations to a question, you can send feedback directly to Knewton support, and hopefully someone will get back to you shortly with a fix to your issues. I hope you understand that you will not have the instructor cheat option that fills in correct answers for instructors only for demonstration purposes, so I'm not going to be using that here. But you will see or be able to find a more instruction option. So if you're working on a problem, having trouble, you don't really remember what the material is for that objective, click on more instruction or open up the more instruction option, and you should be taken to reading to do or videos to watch or both related to that objective. And hopefully with all that instruction available, you can get through the assignment questions more easily. All right, so our first objective, use sigma notation to calculate sums and powers of integers. So the first question says use properties of sigma notation and rules for sums of powers to evaluate the following sum. So we have now, this is called sigma notation. This is the Greek letter sigma. And I'll write this out and identify some things. So we have, when you see this sigma symbol, it means you're going to be adding, taking a sum. You have the sum of this expression, values of this expression, where the first input is k equals 1, and then the last input is k equals 6, and you have all the values of this expression for inputs between 1 and 6 increasing by 1 each time. So I'll write this out and explain more. So again, this is called sigma. Looks like a big E. So again, when you see this symbol, you're going to be adding things. So again, they're calling this, sigma notation. All right, so before I write that one out, the one from the problem, I'll write up a pretty general one. So you have the sigma notation, you see the Greek letter sigma. Then beneath and above, you'll see some values of a particular variable. Now in this problem I'm looking at, it's the letter K. It can be whatever letter you wish. Now I'm going to use the letter I here because this is usually referred to as the index variable. So I'll do what they're doing in the problem there. Say I'm going from I equals 1. So you have some initial value, some first value of this index variable at the bottom, and then an ending value or last value up top. Now I'm just gonna put the letter N for number up here. So there's I equals 1 to I. It's implied to be I equals N, so they don't write it again. And then next to the notation, right to the right of the sigma, you'll see a function, say f of this index variable. Now this is typically denoted as a term of a sequence, so you'll see like a lowercase letter with a subscript of the index variable, so like a sub I, but it's still just a function, some expression that depends upon this index variable. So again, what this represents is a sum, where I plug in the lowest value first, so in this case it would be 1, and then add, and then as you go term by term, the value of the input, the value of this index variable, increases by 1. So the next term, I started plugging 1 in at first, and then I plug in 1 higher, so then 2, then plus, and then f of 3, and then plus, and you keep doing this until you get to that top value above the sigma notation, that last value. So I'd end up here with the value of the function at I equals, n minus 1. That's 1 before the end. And then the final value, plug in the value I equals n. So it's just a big sum. That's really all. So in this example we're seeing, and I'll get to these rules for sums of powers and properties of sigma notation in a minute. But we're asked to find the following. You got the sum from k equals 1. So now the index variable, the variable expression depends upon is this k variable. And then the upper value here is 6. And the expression we're plugging into is 2k squared minus 3k minus 2. So again, you could think of this as just some function of k, f of k, or again, you might see the notation for terms of a sequence, which is typically some lowercase letter with a subscript of the index variable, a sub k. Either way, it's just some expression that depends on the index variable. So, what this represents, now the long version of this, I could write out, first I'm plugging in k equals 1. So it's 2 times 1 squared minus 3 times 1 minus 2. There's the value of this expression when k equals 1. And then I'm adding to this, right? It's a sum. And then I increase the value of the index variable by 1 each term. So the next part of this sum, I'm plugging in k equals 2. So now it's 2 times, 2 squared minus 3 times 2 minus 2. And I keep doing this, plus plug in k equals 3, so 2 times 3 squared minus 3 times 3 minus 2, plus, and then plug in 4 for k, 2 times 4 squared minus 3 times 4 minus 2, plus 2 times, and then plug in 5 for k, right? 5 squared minus 3 times 5 minus 2. And then you end once you've hit that top value. So when k equals 6, so this will be the last part of the expression I'm going to write. So 2 times 6 squared minus 3 times 6 minus 2. Now, this is great and everything, right? It is what this represents. But this is quite a long-winded way of doing this. A little tedious. And it's not wrong, when k equals 1, 2, 3, 4, 5, and 6, this is 6 terms. The number of terms in the sum, so like the number of times you do this, it's going to be the top value of the index. So again, let's call this the upper limit. So upper limit 6, and this value down here, the lower limit. So it's the upper limit minus the lower limit, and then plus 1, because this upper limit minus lower limit just tells you how many more terms you need to go from the first one to get to the top one. So you got to add 1 to also count that bottom one. All right. So this is 6 minus 1 is 5, plus 1 is 6, and you see there are 1, 2, 3, 4, 5, 6 times I did this in this expression. Now I'll box this in. It's good to know. Now, whereas to evaluate this, right, state the value of this sum. So I could go through each one of these, all right, and find the value. And I'll do that, but then I'm going to show you after a much quicker way. So I'll do it the long way first. So again, 1 squared is 1, that's 2, minus 3 is negative 1 minus 2. So this is, negative 3 for that first term, plus this is 8 minus 6 minus 2, so that's 0. Then plus, and then 9, 18 minus 9 is 9, minus 2 is 7, plus, and then 16, times 2 is 32, minus 12 is 20, minus 2 is 18, right? So this term is 18, plus, and then this term, 50, right? 5 squared is 25, times 2 is 50, minus 15 would be 35, minus 2 is 33, and then finally here, plus, 6 squared is 36, times 2 is 72, then you have minus 18, minus 2, So 72 minus 20 for 52. And you put all these together and you got, 52 and 18 make 70. 33 and 7 make 40. 70 and 40 is 110. Minus 3 is 107. So this is the answer. That's what they want from us, to evaluate this sum. But they, in the instructions, right, it asks you to use some properties of sigma notation and some rules for sums of powers. So we'll come back to the answer again here, but let me put up some properties that they're talking about. So properties of sums, properties of these sigma notation expressions. So one of them they'll bring up, and I'll have the lower limit be 1 for the value of the index. And it doesn't always start at 1, but for a lot of these, the lower limit's going to be 1, you'll notice. And you don't have to start at 1, though, just please understand that. You may come across summations that start at different values than 1. So if I'm doing the sum from, again, say I for index, I equals 1 to n of, and then the expression doesn't have I in it at all, say it's just a constant. So again, C is a constant here. Now this still tells me to plug in 1, plug in 2, plug in 3, plug in 4, all the way up to n. So, but no matter what I plug in for I, this has just got a value of C. So it'd be C when I is 1, plus C when I is 2, plus C when I is 3, all the way up to plus C when I is n. And I told you this number of terms would be n minus 1 plus 1, right? Upper limit minus lower limit plus 1 is how many things you're adding. So this would be n times. You have n terms of C. So the sum from 1 to n of just a constant is that constant times n. All right, so I'll bubble that in. Another one is if you have a sum, again, from I'll start from I equals 1 to n, and doesn't have to be 1 and n all the time, of an expression that has multiple terms. So let's say f of I plus or minus, as long as it's a sum or a difference, say g of I, which they may write as a sub I plus b sub I in the sequence notation. Either way, you have a function, an expression that depends on I, plus or minus, and then some other expression that depends on I. Almost like your integrals, which you're going to see these tied to integration later. But like your antiderivatives and integrals, if you have an expression that is a sum or a difference, you can just do this separately term by term. So this should be equivalent to the sum from I equals 1 to n of these f of I parts of the expression, then plus, and then the sum from I equals 1 to n of the g of I, and the next term. So you can go term by term and evaluate the sum term by term. Then you had a constant multiple rule, again, just like with like antiderivatives and indefinite integration that we've done in previous videos if you've been following along. So again, if I had the sum from I equals 1 to n of some constant, so again, I'll use C for some constant. Now this will be a coefficient. of some expression depending on I. So say c times, some function of this I variable. Well, again, it would be c times f of 1 plus c times f of 2 plus c times f of 3. Every single term would have this common factor of c. So you can pull that out, factor that out from the expression. So pull the constant out, c times, and then you have the sum, of just these f of I terms. So that's pretty much all we can handle at the moment. Another one they put up is that you can split up sums. If you add from 1 to n, you can add from 1 to m, and then m plus 1 to n, but hopefully that's pretty straightforward. And then these rules for sums of powers that they bring up, and we'll bring it back here to that first question. I'm only going to put up the ones we need. So for sums of powers, so if I were to add, say sum from I equals 1 to n of just I. So this is I of the first. So that would be just simply 1 plus 2 plus 3 plus, right, and then all the way up to where I replace I with n. Well, there's a nice little formula for these sums of powers. So it's the number of terms, so it's just n, right? There are n terms here, multiplied by the sum of the first and last term, so n plus 1, and then this gets cut in half. So again, we're going to use that eventually up here. And some other power I see in this problem up here is some expression squared. So let me put up the formula for that. Now you can memorize these if you wish. There's also ways to prove them. I'm not going to go waste too much time doing that here. Now if I'm adding up the squares, right, this was the sum of first powers of integers, of whole numbers. So let's say I'm adding up I squareds. So this would be 1 squared plus 2 squared plus 3, 2 squared plus 3 squared plus 4 squared, all the way up to plus n squared. So 1 plus 4 plus 9 plus 16 and so on. And this has a nice closed form, they say, a nice simple expression to give you the value. And this ends up being n, the number of terms again, times n plus 1, then times 2n plus 1, all in the numerator, divided by 6. All right, so I'm going to keep these up, or I'm not going to keep them up, but like they're going to be used in this first problem back here. So like, look, here was the first problem that we were given. We had the sum from, k equals 1 to 6 of 2 times k squared minus 3 times k minus 2. So when they're saying, use the properties of sigma notation and the rules for sums of powers to evaluate this sum, this is what they're talking about. So I've got an expression here that is a sum difference, right? So I can split this up, go term by term. So this is the sum from k equals 1 to 6 of this first term, the 2k squareds, then minus, and then the sum from k equals 1 to 6 of this next term here, the 3k terms, and then minus again, and then the sum from k equals 1 to 6 of just this, this last term's a constant term, these two terms. So this is what I can kind of distribute it almost. It's almost like distributing, even though they don't call it that. That's that sum property I put up earlier. You can go term by term, apply the symbol to, spread it out term by term. And then each of these terms has some coefficient involved. Now this last one is just a constant, so I'm going to leave it that way. But these first two have constant multiples of some function of k, right? The index variable being k here. So I can factor those out, right? That's that constant multiple rule I put up. So the first one I'll have 2 times, and then the sum from k equals 1 to 6 of just these k squared terms, then minus, and then the next one, there's a coefficient of 3. I'll factor that out, 3 times the sum from k equals 1 to 6 of just the k terms. And then again, this last one, I mean, you could pull the 2 out if you wish, so I could do that, pull the 2 out. But if I do, there's still a constant left over there. There's still a 1, 2 times 1 is 2. There's still a 1 in there after the sigma notation. All right, and then each of these has, a nice special formula to help you evaluate it. Each of these summations. So this first one with the sum from k equals 1 to 6 of the k squareds, that's using this formula, right? From 1 to n of the I squared. So we'll just replace I with k and n with 6. This is representing 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared. So again, replacing n with 6 in this formula, we end up with the following. So this would be 2 times, 6 times 6 plus 1, so times 7, times, and then 2 times 6 plus 1, that'd be 12 plus 1, so 13. And then that product gets divided by 6. So that's using, we'll simplify that in a second, but that's using one of those, sums of powers formulas. Then the next one, I got minus 3 times, and then this sum from k equals 1 to 6 of just the k terms. I'll be using this first power one up here, right? Instead of I got k, and instead of n, I got 6. It's 1 plus 2 plus 3 plus 4 plus 5 plus 6. So I just replace n with 6 in my formula here. This ends up being 6 times, and then 6 plus 1 is 7. And then this gets divided by 2. And so again, using the formula for the sum of first powers. And then minus 2 times, and I talked about the sum of a constant, right? This sum from k equals 1 to 6 of 1, that would be 1 plus 1 plus 1 plus 1, plus, 6 times. There are 6 terms here, 6 terms of 1. Well, that's just 6 then. So this sum is just, 6. All right, then we simplify some things. Now, you'll notice that in the first expression there, first part of this, you got 6's would cancel, and then here, 2 goes into 6 3 times, that becomes a 3, and then we got some nice stuff. 7 times 13 is 70, and 21, that's 91, times 2 be 182, then minus 3 times 3 is 9, times 7 is 63, and then minus 12. So 182, minus 12 would be 170, minus 63 would be 107. Right, which is exactly what I got writing it out the other way, right? Just actually writing what all the terms look like and adding them up, right? Got 107. So however you decided to do that one, you would have gotten 107. Now, if this was a larger number, right, if this was from 1 to 100 or something, I would have definitely done it this way, right, versus this way, because if it was 1 to 100, I don't want to write out 100 of these, So that's why these, sums of powers formulas can come in handy. And then one other thing I want to show you, just to make things quicker later. I know it's dragging out this first question, but you can do a sum very quickly also. Check yourself in Desmos, right? This is again free online graphing calculator. Used it in plenty of other videos. So if you go to the calculator, just type SUM, sum. All right, the sigma notation shows up. Now their index variable is n. All right, so careful with that, right? So the expression I put after it should, depend on n, have the letter n involved. So, change k to n in the problem we had. So I'm going from n equals 1 to 6 of, and then the expression was, 2k squared minus 3k minus 2. So I'm going to change that to 2n squared uh, minus 3n minus 2. And, there you again are seeing the value of 107. So it's very nice, does things very quickly for you if you're in a pinch. So after all that, this is 107. All right, then submit. Now, once you've submitted an answer, it'll tell you whether you're right or wrong, and then give you some sort of answer explanation. Definitely read through these. If you got something correct, maybe glance through it, see if they did things in a way that you like better, and then, use that method for future questions that are similar. Definitely read through these if you got it wrong. And hopefully you can figure out where you went wrong and fix your mistakes for future questions that are similar. Okay. All right, so this one is the other objective in this heading with the sigma notation. So write a series of numbers using sigma notation and use the properties. Those properties I had mentioned, those were just some of them, just a few of sigma notation. So look, this is evaluate the sum. Enter an exact answer. So we're given the sum. From this time, the index variable is j, right? So from j equals 2 to 6. So again, notice it's not starting at 1. So those formulas I put up earlier for the sums of powers, you're not going to use those here. I mean, you could, but then you have to remember to take away the term that has 1. And I'll explain. I'll show you what I mean. So we'll do this a couple ways again. So the expression that depends on j is this 4j minus 3. Now there are only 5 terms here, right? Upper limit minus lower limit is 4, plus 1 is 5, so there's only going to be 5 terms. That's not so bad, right? When j equals 2, 4 times 2, 8 minus 3, that's 5, plus, and when j equals 3, we're just going to keep adding 4 each time, so that'll be 9, plus when j equals 4, it's 13, when j equals 5, it's 17, and finally when j equals 6, that's 21. And adding these up, 21 and 9 is 30, 13 and 17 is another 30, so that's 60, and then 5. So 65 is your total. Now, I told you about the formulas. So remember the sum Now, if it was from j equals 1 to 6 I see j to the first in there. So if I had this, so again, this is 1 plus 2 plus 3 plus 4 plus 5 plus 6. So one of those properties I mentioned earlier is that you can split a sum up. You know, so if I want to have the sum from j equals 2 to 6 show up, well, I take my sum from j equals 1 to 6 and then just take off the term, there's the term when j equals 1, right? 1, and then plus, and then the rest of it, right? The rest of this would be the sum that's going to show up when I use properties here later. The sum from j equals 2 to 6 of these j terms. So this and this mean the same thing. They both represent this sum of 1 to 6. Now, this sum from j equals 1 to 6, I showed you a formula for that earlier, right? If it started at 1, and this would just be 6 times 6 plus 1 divided by 2, which is, 3 times 7, that's 21. So the sum from 1 to 6 is 21 of these j's. That means the sum from 2 to 6 is, 21 minus 1, right? I would subtract 1 from both sides here. So then the sum from j equals 2 to 6 of just these j to the first power terms would be 20. And I can use this, right? This isn't the answer or anything, but I can use this when I go about applying properties. Right, so if I go through and use properties, hey, this is a difference, so I can go split this up, go do the summation of each term separately, pull the constants out. I would have 4 times, and then the sum from j equals 2 to 6 of these j to the first terms minus, and then 3 times the sum from j equals 2 to 6 of just the number 1, right? And that, pull 3 out of that, that's 3 times 1. And we just saw down here, through all this, that this sum from j equals 2 to 6 of j to the first power terms, that's 20. So this is 4 times 20 minus 3 times, and then this is, remember I said earlier, there are 5 terms here, 6 minus 2 plus 1. So this would be 1 plus 1 plus 1 plus 1 plus 1. It's 1 5 times. So that's 5. So we end up with 80 minus 15, which is, 65. So either way you did it, you end up with 65. Now again, there are only 5 terms, so I would suggest, just doing it this way, the way I first did it, and it's a lot quicker than trying to figure out how to work the formula into this for sums of powers. And then once again, you can always, and I might do this later again to speed up some time, but you can always go to Desmos, type in the word sum. Again, the index, they're going to automatic have index 2, index is n. So this was from, n equals 2 to 6 of 4, it was 4j minus 3, so I'm going to call it 4n minus 3. And you see again here, 65. So 3 different ways of doing it, showing that the answer has to be, 65. Great. All right, so this one has, now this would be 9 terms. Oh, but they're not asking for the sum. So I'm not even going to write that out, Just fill in, it says determine the first 2 terms and the last 2 terms in the sum given below. So I have the sum from k equals 1 to 9 of 5k plus 2. So the first 2 terms are when k equals 1. So that'd be 5 times 1 plus 2, that'd be 7. And because you got this k times 5 here, right? Every time you increase k by 1, the value of the term will increase by 5. So the next term would be 12, right? 5 times 2 plus 2, and so on. Now they say those are the first two terms of the sum. And these last two are when k equals 8 and 9, right? The last value has to be when k equals 9. When k equals 8, this is 40 plus 2, so 42 would be the second to last term. And then when k equals 9, you got 45 plus 2, 47. Okay, so they don't actually want the whole sum, what this equals. They just wanted me to fill in the first two terms of the sum and the last two terms of the sum. Very simple. All right, so this one has me using rules for sums of powers. So notice, all right, so I told you this earlier, right? If you're going to use rules for sums of powers, they should start at 1. So this one does not start at 1. So I'm going to have to manipulate this the way I did earlier, in an earlier question. So here's what we were given. So we have the sum from its I equals 4 to 16 of 9 times I. Now, remember, I can pull constants out, so this is 9 times the sum from I equals 4 to 16 of just these i's. So now I want to focus on this. All right, I want to focus on this. Now, we saw earlier, and we saw the sum from I equals 1 to 16 of I. That would be, 16 times 17 divided by 2. Right, again, starting at 1. This is 1 plus 2 all the way up to 16. So that's 8 times 17, right? 80 and 56, 136. Now, I told you, all right, this is only for when you start at 1. So this is 1 plus 2 plus 3, and now you see this is when I equals 1, I equals 2, I equals 3. So the rest of it would be what I have here, plus the sum from I equals 4 to 16 of these I terms. And 1 plus 2 plus 3 is 6. So then to get the sum that I want, I just need to subtract 6. So, the sum from I equals 4 to 16 of these I to the first power terms is 130. All right, and again, that's one way of going about it. I don't think they go into substitutions here, but you could make substitutions to turn this into something that starts at an index value of 1 instead of 4. But I'll look through the answer explanation after this, see if they do any substitutions, and then we can do that in a future question. But for right now, this is good. So this ends up being 9 times, and then we saw just now, this sum from 4 to 16 is 130. And 9 times 13, 90 and 27, that's 117 with a 0, so 117 with a 0, that's 1,170 for the value of this sum. And again, you can check back in Desmos. And again, if you want to save some time, still practice, doing some of these things on your own by hand. But then, once you feel you got it down, I have no issue with you going to Desmos and just doing it real quickly there. So yeah, see, they took the sum from 1 to 3. That was the 6. Subtracted it away. Yeah. All right. So no substitutions there. Okay, so some more property stuff. So notice again, I was using function notation. I told you a lot of the times they're using the sequence notation where you had this A with a subscript of I or B with a subscript of I. Again, this just means some function of I. You have an expression depending on the index variable being plugging values into those and adding them up. All right, so we're given the following sums. The sum from I equals 1 to 140 of these A sub I terms is -3. And then the sum from I equals 20 to 140 of these A sub I terms, the same expression, AI and I, is -31. So what would be the sum from I equals 1 to 19 of 4 times A sub I? So this is kind of similar to the last question. Again, you got to split your sum up. So we're asked for the sum from I equals 1 to 19 of 4 times these A sub I terms. Well, I got a constant multiple, so I can factor the 4 out. So this is 4 times, and then the sum from I equals 1 to 19 of just the A sub I terms. Now we were given the following. One of these was the sum from I equals 1 to 140 of these A sub I terms. So that's A1 plus A2 plus. Now I'm going to go up to, we need to figure out what happens at 19 here. So plus A sub 19 and then plus A sub 20 all the way down to, A sub 140. So again, this would be represented as the sum from I equals, starting at 1, ending at 19 of these A sub I terms. And then this would be represented by the sum from I equals 20 to 140 of these same, A sub I terms. We were given that this value, the whole sum from 1 to 140 was -3. We were given that this value from 20th term to 140th term was -31. So to find this, right, this is part of the expression I want to find the value of. I just need to add 31, right? This is plus -31. So if I were to add 31, we'd get, -3 plus 31, that's 28, right? So this sum from I equals 1 to 19 of these A sub I terms would be 28. And that's going in my expression up here. So this is 4 times 28, which is, 80 and 32. It's 112. Now this isn't really anything you could enter into Desmos because you don't know what the expression A sub I is. You don't know what that function is. So this is kind of something you'd have to do by hand. So 112 must be. So now it's just about a matter of filling in values in sigma notation, the lower limit, upper limit, the expression, right, the function of the index variable, and finally the sum. So write the following using sigma notation and then actually find the sum. All right. So they gave us these values of k, right, from 2, 3, 2 to 5. So lower limit, the starting value of k is 2. That's going down here. The last one is 5. So 2 to 5, lower limit, upper limit. The expression is given as, again, this function of the index variable that they call k, 2 to the k minus 1 power, get out of the power, plus 4. And then I would, add these up. Now, the sum of powers of 2, now again, when k equals 2, this would be 2 to the 2 minus 1, that'd be 2, 2 to the first. So it'd be 2 plus 4 when k is 3, plus 8 when k is 4, and then plus 16 when k is 5. Maybe I should write this out. But there's only 4 terms here, right? 5 minus 2 plus 1. So we have the sum from k equals 2 to 5 of these 2 to the k minus 1 power and then plus 4. So again, these powers of 2, again, would be 2 plus 4 plus 8 plus 16. That's it. And then again, you'd have 4 times, right? So plus a 4 times 4. And this remember the sum of a constant is just that constant times how many terms there would be. And it's 5 minus 2 plus 1 terms. So that's another 16. So, this is 14 here, 30, 16, 30 and 16. So 46 is the total. So that's going on the right side here. All right, great. So those rules of sums of powers are coming back. All right, so again, this isn't starting at 1, right? Those rules for the sums of squares, sums of powers, are all starting at 1. So this has the sum from I equals 6 to 14 of 9 times I squared. So again, I'm going to pull the 9 out, constant multiple. And now we're going to focus on the sum from I equals 6 to 14 of these I squareds. Now that is only 9 terms, right? 14 minus 6 is 8, plus 1 is 9. So you could probably do this that wouldn't take too long to do by hand. The squares might get a little, the 14 squared is 196, right? The numbers get a little big, but not that big. But let's recall that the sum from I equals 1 to 14 of these I squareds, and there'd be 1 squared plus 2 squared plus 3 squared all the way up to 14 squared. And that's 14 times 14 plus 1 times 2 times 14 plus 1, so 28 plus 1 would be 29, divided by 6, and we'll simplify that in a second. Now, that's the sum of 1 squared to 14 squared. This one we want in our expression up here is only from 6 squared to 14 squared. So I need to split this up to the sum from I equals 1 to 5, right? Do 1 squared to 5 squared, and then add on the rest of them, which would be the sum from 6 squared, 14 squared. And if it starts at 1, we can use our formula again, right? That's sum from 1 squared to 5 squared. That would be 5 times 5 plus 1, so 6, times 2 times 5 plus 1, so 11, divided by 6. So again, and then we can solve this equation here for the expression, this sum that's in our expression up here from 6 squared to 14 squared. All right, so doing some simplifying, 6 is 2 times 3, and 2 goes into 14 7 times, 3 goes into 15 5 times, and 7 times 29, 140, 63, so that's 203 times 5 would be 1015, so this is 1015 over here equals, and then over here this is just 55. All right, 6's cancel, 5 times 11. So I would subtract 55. So after doing that, subtract 55, this sum from 6 squared to 14 squared, subtract 55, then minus 15 for 1,000, and then minus another 40 for 960. Okay, so this is going in this expression, right? So we end up with 9 times 960, which, 9 times 900, I'll just do 9 times 96. That's 100 minus 4, so 900 minus 36 would be 864 with a 0, 8,640 should be our sum. Now, I really want to double check this just because of all the arithmetic that was going on here, just to be sure of myself. So I'm going to go to Desmos here and just type that in. We had 9, n, remember the index in Desmos is n when you type the word sum. So instead of 9i squared, I got 9n squared. And the lower limit on our index was 6. The upper limit on the index was 14. Yes, and it is correct. It verifies my answer earlier, 8,640. Okay, so this would be similar. So again, this time though, you'd have 4 pulled out, and they'd be adding up just the first powers from 3 to 17. Now from 1 to 17 would end up being 17 times 18 divided by 2. So 17 times 9, which would be 153. And then you would take away the sum from just 1 to 2, and that'll give you from 3 to 17. So again, 153, then minus 1 and 2, so minus 3, 150. This is 4 times 150, which will be 600. And I did a lot of mental math there. Let me just double check that. So this was from 3 to 17 of, 4n. Yeah, 600. Very good. All right. Okay, so those properties of summation notation and, sums of powers and whatnot, those objectives are done. So now we're going to move into the title of the assignment in the approximating areas. All right, so now these 4 objectives under this heading. So this is where we're going to be given some function, some continuous function over an interval, and asked to estimate, approximate the area taken up between the curve and the x-axis, over that interval. And we'll be doing this with rectangles. So that's the first objective thrown at me here. Approximate the area under a curve using rectangles. So look, we got the graph of a function is shown below. So this looks like one of those interactive ones. Has a blue curve, right? So the function is this blue curve, wavy curve. Create a visualization of a left endpoint approximation for the area under the curve on the interval from 1 to 7 using 8 rectangles. Slide the orange points horizontally to adjust the endpoints of the interval. All right, so we need to be from, it says the interval's from 1 to 7. So I'm going to move the left end of the interval from 1 to 1, the right end to 7. So now we're looking between 1 and 7. Use the vertical slider on the right side of the graphing window, the blue movable point, to control how many rectangles your approximation for the area will have. They asked us for 8 rectangles. Right now it's n equals 4. So you see 4 rectangles shown up here. We want to move that up to 8. There we go. So they took this interval from 1 to 7, divided it into 8 pieces. Now 7, that has a length of 6 units, right? 1 to 7 is 6 units long. And if you divide 6 by 8, you get 0.75. So that's what this delta x is. 0.75 is how wide each rectangle is. The value of each rectangle's width, delta x, will also be shown, as I stated. Finally, drag the black movable points to adjust the height of each of the rectangular boxes. So they said use the left endpoint approximation. So that means in each of these sub-intervals, right, each of these 8 pieces that this interval from 1 to 7 is broken up into, so we got the widths of each rectangle, right, 0.75, plug in the left end of each piece. So I plug in the left ends and get an output on the blue curve, and that'll give me the height. See how it changes the height of the rectangle. So I plug it in, getting a nice estimate to where that black point is on the curve. And I do this for all the left ends of the rectangles, right? So maybe about there. Looks like about here. This one about there. This one. Again, the left ends, just try to get them on the blue curve or as close to being on the blue curve as possible. Looks all right. Okay. And that doesn't look too bad. So you see all these green rectangle areas now. You have the areas of these rectangles are 0.75 times, whatever the height is at each of these left endpoints. And then you would add all these areas up and get, an approximation to the actual area under the curve. You see it's not exact, right? There's some missing pieces. It overestimates in some places, underestimates in other places. But it is still an estimate, right? Still an approximation of the area under the curve to the x-axis. I think that looks pretty good. We'll see what they say. Yeah, I guess it was close enough. So looks good. And that's it for that one, right? Just I don't know if they actually do the plug-in. Maybe they do, but they don't want the actual area, right? They just have you fill in a picture. Okay, so now we're asked to find an upper and lower sum of some function. So an upper sum is something that should overestimate the area, and a lower sum should underestimate the area. So we'll see when we get into this. All right, so the graph of the function f of x equals 4 minus 1/4 x cubed, or x cubed over 4, is shown below as a blue. Oh, so it's another interactive one. Okay. Create a visualization of an upper sum for the area under the curve on the interval from -2 to 2 using 4 rectangles. So the interval, so it's the same as the last one where you move the orange points, to make the interval -2 to 2. So -2 to 2, that's a length of 4 units, and they already have 4 rectangles here. So we don't need to change that. And when you see when there are 4 rectangles, they break the interval of length 4 up into 4 pieces. Delta x is 1, right? The width of each rectangle is 1 unit. Now they're asking us to make the upper sum. So again, you're dragging the black points here to move the heights. Now, upper sum means in each of these rectangles, in each of these pieces. So like the first piece here is from -2 to -1. You plug in a value that will give me the highest point of the curve, give the highest output possible, give me the maximum output possible in that piece. So you see from -2 to 1, the highest point is here at -2 on the left end. So I'd plug in a value to give me that height, right? And make sure the height is as high as that highest point in the interval. Again, clearly this should, overestimate the area under the curve. Same thing for the next piece, or you do this for each piece. So from -1 to 0, I would plug in a value that again takes me to the highest point of the curve just over the interval from -1 to 0, and that would again be on this left end. So I'm going to make the height as high as the point as high as the curve is on the left end here. So again, it should overestimate, right? When you're doing an upper sum, you're going to the maximum point in that piece. You're going to the highest point on the curve over that piece. So it should, overestimate the area. Now for this interval from 0 to 1, once again, the highest point looks like on the left here. So I'm going to move it up so that the height of the rectangle is that high as the point is on the left side. And you see it a little overestimation. And then finally, from 1 to 2, again, the highest point of the blue curve over this interval from 1 to 2 is again on this left piece. So it's pretty much just like the left endpoint approximation earlier. Now, the highest point isn't always on the left end. The highest point could be in the middle or on the right end or somewhere in between, right? It just so happened that with this picture, because it was a decreasing function, right? This is this function is going down all the time. The highest point would be on the left. If it was going up all the time, the highest point would be on the right, and my upper sum would look a little different. But that should be good for the, oh, well, okay, I think I have to pick left endpoint approximation. Let's read the instructions carefully here. Yeah, I'm going to change this. I said the highest points are always on the left, so we should change this to left endpoint approximation. And now I see it moves those dots to the highest points, those left endpoints, but still, you would move the heights up to be as high as the highest point over each of those pieces to obtain an upper sum. Okay, good. So this one okay, so we're given a graph of a function. Estimate the area under the curve on the interval from 0 to 4 using the right endpoint approximation and only 2 rectangles. So from 0 to 4. All right, so I'm going to draw as best I can the look of this thing, this function, just from 0 to 4. So here's what we have. So I'm going 0 to 4. Now they said using 2 rectangles. So I take this length here, 4 minus 0, divide this by 2, and that'll be the delta x, which is going to represent the width of each rectangle. So the width of each rectangle, 4 divided by 2 is 2. So let's break this up into pieces of length 2. So 0, 2, and 4. And and then they said use right endpoints. So on the graph, the value of the function at 2 is 4. So I'll plot that point. So here's the point 2, comma 4. And then on the graph, we're given the value of the function at 4, which is, again, the right endpoint of this first piece is plug in 2. The right endpoint of the second piece is, 4, plug in 4, is 4, 1. So I'll draw, again, a very rough estimate of what this thing looks like. So it's starting here at 0, 2, it looks like, and it goes up to like 1, 5. And then again, comes back down here through 2, 4. And it passes through 3, 2. And then to 4, 1, something like this. This is the graph of the function, say y equals f of x. Right, so again, the area, the right endpoint approximate, we're asked to estimate the area under the curve to the x-axis. So I plugged in the right endpoint at 2, of this first interval from 0 to 2, got this point, with a height of 4. So here's our first rectangle with this area here. And you see it almost gives me the area under the curve, right? It actually, it overshoots it here, but then misses all this space up here, but it still is an approximation. Now the area of this rectangle is, 2 by 4, so this is 8 square units. Right, area is 8. And then again, right endpoint approximation, the next interval from 2 to 4 here, I plug in 4, takes me to the point 4, 1, and I create a rectangle with that height. And so here's my next rectangle. And the area of this rectangle is, it's a 2 by 1, so 2 square units. So the total area of these rectangles is, 10 square units. So that should be approximately the an approximation of the actual area under the curve. It's obviously missing some stuff, and it's not perfect, but it does, estimate the area. That's all they wanted, right? Just 2 rectangle areas add together. It can be an approximation of the area, actual area under the curve. So area under the curve, see a little wavy equal sign, is approximately 10 square units if I'm doing a right endpoint approximation. And they might have a picture here. I don't know if they'll have a, yeah, they have a nice picture like that. Okay. All right, so here is determine if a sum will be an underestimate or overestimate. So now these sums, okay, this is just a fancy name for them. These sums of areas of rectangles to approximate area under the curve to the x-axis, Uh, these are called Riemann sums after a German mathematician named Bernhard Riemann. And just know that that's all that means, right? These Riemann sums are just doing what we did on the previous page, these sums of areas of rectangles to approximate areas under a curve. So a left Riemann sum, meaning that I'd be plugging in left endpoints instead of right endpoints or midpoints or something, or it's not an upper sum or a lower sum necessarily, but just plugging in left endpoints to get the heights with 6 rectangles, right? 6 subintervals is used to approximate the area under the curve of, this quadratic function here, just over the interval from 6 to 7. So is the approximation an underestimate or overestimate? Now, it's a quadratic function. You should know or have a rough idea as to what the graph of a quadratic function looks like. So we're given f of x equals, negative 4x squared plus, 64x plus 3. Now this is quadratic, and remember the axis of symmetry would be the opposite of the linear coefficient divided by twice the quadratic, so negative 64 over negative 8, so at positive 8. So the vertex would be at positive 8. And then, if I plug that in, you don't need to though, because and this would be negative 4 64s plus 8 64s would be 4 64s, which would be 256 plus 3. It's really high. It's 259, right? So it's like 8. You didn't really need to find this, but 8, 259. What you do know though is that this would be a parabola opening down, right? The lead coefficient is negative. So again, some parabola opening down. Now we're supposed to be looking at this over the interval from just 6 to 7. So this area right here is what's being talked about. Okay, this area here under the curve to the x-axis. Now notice how the function is increasing on this interval. So look, when a function's increasing over some interval, so I'll just put up a few pieces here. So let's say a function's going up like that. If I use left endpoints, so for each of these pieces I put down here on the horizontal axis, if I plug in the left ends and make rectangles with those heights, I'll get rectangles that underestimate the area under the curve. See this missing area here. Same thing here. I plug in the left end, make a rectangle with that height, and it's an area that's coming in underneath the entire area. It's underestimating. Same thing here. Right? Plug in the left end, make a rectangle with that height, and this area is definitely smaller than the area under the curve. So for increasing functions, these left Riemann sums, again, Riemann sum, that's an n. Left Riemann sums underestimate the area. Now, if they asked for a right Riemann sum, you would plug in the right end and make a rectangle. So you see how that would overestimate plug in the right end of the interval, make a rectangle, and that would overestimate, right? Plug in the right end and make a rectangle, and it overestimates. The right Riemann sums overestimate. That's for increasing functions. It's just the other way around for decreasing functions, right? So if I have a decreasing function over some interval with so many pieces in it, if I plug in the left end and make a rectangle with that height, you get more area, right, than the actual area under the curve. So it's just the other way around for decreasing. So I'm not going to write that. Just for decreasing functions, left Riemann sums overestimate and right Riemann sums underestimate. So here, I don't even need to know how many rectangles I'm making. They told me it was a left Riemann sum, and I know based on what I know about quadratics that we got a piece of the curve that's going up, that's increasing. So this left Riemann sum would underestimate the area under the curve. And they probably explain all that. And again, increasing, decreasing just switches it up. Yeah, and they figured with the derivative that it would be increasing, right? I just drew a picture. Now, if it was a different kind of function, if it wasn't quadratic, I would have probably looked at the derivative over the interval just to see if it was positive or negative, right? Remember, if the derivative's positive over some interval, it's increasing. If the derivative is negative over that interval, it's decreasing, right? So, if it were a different kind of function, I would have looked at the derivative instead of trying to draw a picture. All right, so here's another one. Now this was using a midpoint. So we saw left end point, right end point. This is just, plug in the point in the middle of the interval and get a height. So another graph here. So for the following graph, right, estimate the area under the curve in the interval from -3 to 3 using the midpoint approximation and only 3 rectangles. All right, so like I did before, I'm going to do my best to roughly draw this on paper. So we have this, again, -3 to 3. So from -3 to 3. And we want to make 3 rectangles, they said. So the change in x, the width, and how wide each rectangle will be. You take the length of the interval, which would be 3 minus -3, right, which is 6 units long, and then cut this into 3 pieces, right? We want 3 rectangles. So that's 6 divided by 3. So each of these will be 2 long. So -3 will be the left end, and then -1 will be the right end of the first piece, and then add 2 again for +1. So there's -1 to 1 for the second piece. And then, 1, 2, 3, add 2 again for 1 to 3 for the third subinterval. So they're asking me to plug in the midpoints. So in this first piece here, from -3 and -1, right, the midpoint would be -2, again, the value in between. And then in the next subinterval, the midpoint will be 0. And then in the interval from 1 to 3, the midpoint is 2. So I'll get some points there. Now on the graph of this, at -2 looked like it had an output of 4. That's not the scale or anything. So there's -2, 4. And then at 0 has a value of 7. And then at 2, then the third midpoint here looks like it has a value of 7 again. So I'm just going to draw the rectangles. So again, in this first interval, I'd plug in -2, get an output of 4, and then just create a rectangle with that height and this delta x width, right? This width of 2 here, where -2 is the midpoint. So again, this area, so I'll just put A equals. The area of this rectangle, again, this is the 2 by 4, so this is 8 square units. Now, if I were to draw the curve in, again, you would definitely see that this is not the actual area under the curve. It just estimates it. And then for this -1 to 1 piece, I plugged in the midpoint, plugged in 0, got 7. So I get a height, make a rectangle with this width and a height of 7. All right, so the area of this rectangle, all right, this is a 2 by 7, that's 14 square units. And then another one that's going to be 2 by 7, right? Because again, I plug in the midpoint of this 1 to 3 interval, that's 2, plug that in, get 7. So there's another 2 by 7 rectangle with an area of 14. So the area under the curve, right, is approximately 14 plus 14 plus 8. That's 28 plus 8, 36, square units is what I'm going to be entering. So again, that's not the exact area from over the interval from -3 to 3 under this curve, but it's a nice approximation. All right, so 36. And there's the picture that I was going to try to draw, but I was like, I didn't feel like putting the curve in. It's like eyeball things. All right, so once again, overestimate, underestimate. It's another quadratic. Now I could do the thing with the derivative, right? The derivative of this would be negative 6x plus 18. Now negative 6x plus 18, that'll be equal to 0 at x equals 3. And to the left of 3, it'd be positive. To the right of 3, for values bigger than 3, it'd be negative. So this curve, this is a parabola opening down again. So again, to the left of 3, it would be increasing. To the right of 3, it would be decreasing. This is, the interval from 1 to 2. So increasing again. And they asked for a left Riemann sum. So like I stated earlier, right, you're plugging in left endpoints on a piece of curve that's going up, that's increasing. Those rectangles are going to underestimate the area. So another underestimate. All right, so another midpoint here. This is another one where you're moving things around. So again, the interval from -5 to 1. So I'll move the orange points, -5 to 1. They want 5 rectangles. No, 6 rectangles, 6 rectangles. So now I got 6 rectangles. And they already have the midpoints, the middle values plugged in. Now I just need to move them to the curve, right? Make sure that the height is the value at this midpoint on the curve. So there's about there, and let's move the midpoint here up to, again, beyond the curve as best you can. That looks pretty good. Yeah, a little closer. Maybe about there. So there. All these areas added up are approximately the area under the curve over this interval from -5 to 1. Oh, sorry, -5 to -1. Ooh, glad I caught that. All right, so I got to remove these, right? It's from -5 to -1. So there's the interval from -5 to -1. Again, I'm going to move these so that the midpoint values are on the curve as best I can. That's not good. It's better. So the black dots on the curve. And that looks pretty decent. 6 rectangles like they asked for. Great. This should be good. All right, cool. All right, another upper lower sum thing. So now this time we have to do it ourselves. There's no drawing. But this is a cubic, a pretty basic transform cubic. That'll be a decreasing function. So I would use left endpoints. So I'll do this. We'll take the interval from -1 to 3, break it up into 4 pieces, right? So we're going to make 4 rectangles and plot points on this function. So again, I think I might just do what I did in the last example here and just draw the rectangles. Oh, actually, no, we need to know the upper sum. So I need to know where the highest point is over each piece. Now, f of x equals, 4 minus, this is 1/10 x cubed. Now the derivative of this will tell me that it's a decreasing function, right? If you take the derivative of this, it'd be -3/10 times x squared. And this is never going to be positive, right? Right, no matter what you plug in, no matter what real number you plug in for x, it'll be a negative number times some non-negative number. So it'll be negative, well, it'll be non-positive, never positive. So that means, f is a decreasing function or non-increasing. So I'll use that information to help me when I plug in these values. So we're going from, they asked us to do this over the interval from -1 to 3. So let's say that's over here. And they want us to use, 4 rectangles. So the widths of each rectangle should be 3 minus -1, right? The length of the interval, broken up into 4 pieces. Now that's just 4 divided by 4, that's 1. So -1 to 0 for 1, 0 to 1, 1 to 2, and 2 to 3. Now because f is decreasing, and we're asked for an upper sum, if f is decreasing, going down all the time, the highest point will be at the left end. Right? The highest points are left end points. So that'll be, so I'm just going to plug it. So I'm just going to do a left endpoint approximation here. So for each piece, plug in the left endpoint. So the area, you know what? So the area is going to be the value of f at -1 times, 1 delta x. That'll be the height. So f at -1 would be 4 plus 1/10. So 41/10, 4 and 1/10. So plug that in, and then we get this first rectangle with a width of 1. And again, that left endpoint will be the highest point on the curve coming down. This should, this will overestimate to give me an upper sum. Plus, and then, next rectangle, f at 0 times 1. And again, the width is always 1, and the height will be f at 0. And the value of f at 0 is just 4. So that's, 4.1. This is 4. So I plug in 0, get 4, and then we make another rectangle with a width of 1. And this would, again, this would overestimate the area under the actual curve. and then I plug in, 1 to get the next height, f of 1 times 1. Now 4 minus 1/10, that'd be 39 tenths, 3.9. So I get that, and then get this area. And then finally, plug in 2 times 1, right? Height times width. Now 2 cubed is, 8. So that's 40 tenths minus 8 tenths, that'd be 32 tenths. So again, this would be this height, and we get this area. So again, if I had to estimate what the curve would look like, again, being it's a cubic, probably something like this, right? Again, it would be decreasing, flatten out at 0, and then keep decreasing, and something like this. So you see the actual area under the curve is overestimated by all these rectangles, right? This should be an upper sum. Give me the largest possible area of these 4 rectangles over these 4 pieces. So again, this is simply oh no, they said 4.1 plus 4 plus 3.9 plus 3.2. So this is 6, 7.1, 11.2, 15.2, or 152 over 10, which would be 76 over 5, and reduced. As I said, enter a fraction, right? So approximately 76 fifths for all those areas. Great. And they might have a picture. Yeah, they do. So that's, see how that curve is always going down. So again, the left endpoint approximation, the highest point for an upper sum, the highest point over every interval is at the left end. Okay, so this time we're using a right endpoint approximation. So just plugging in the right ends of each piece. So again, now this time, I mean, you can figure these out without drawing them pretty easily. Right endpoints, left endpoints, midpoints. The only ones that'll be tricky are upper sums and lower sums, where you have to figure out, where the highest point over each piece is for upper sums, and where the lowest point over each piece is for the lower sums. But the right endpoints, left endpoints, midpoints are very easy to determine by comparison. So the function we're given is 1/10 times x squared, or x squared divided by 10, plus 1. And we're on the interval from, -6 to 0. And we're asked to do this using, 3 rectangles, right? N equals 3 rectangles. So again, you want to think of the interval. I'm not even going to draw the rectangles this time, but if I'm going from -6 to 0, the width of each piece, right? The width of each rectangle, this delta x, would be 0 minus -6, right? It's right end minus left end. Tell you how long the interval is, that's 6. I'm breaking it into 3 pieces, right? 6 divided by 3 is 2. So the first piece goes from -6, 3 pieces here, -6 to -4 for a width of 2, then -4 to -2 for a width of 2, and -2 to 0. And then these are the right endpoints, right, of each interval. And that's what they're asking me to plug in to get the heights. So the areas of these rectangles, right, the area under the curve is going to be approximately the value of f at the first right endpoint at -4, and then times 2. All right, again, the width is 2 for each of these. Plus, and then the next piece, I'd plug in the right endpoint, plug in -2, again, times 2. And then plus, and then the last rectangle, again, would have a width of 2, and I'm plugging in the right endpoint, plus f of 0 times 2. Now, each of these has 2, in fact, so you could factor that out. I'll put it on the right side here, factor out a 2 from each of these, and then just, add up these function values, f of -4 plus f at -2 plus f at 0. Now, the value of f at -4, and -4 squared is 16, divided by 10 is 1.6, plus 1 is 2.6. I'm going to put decimals for right now. Plus the value of f at -2. -2 squared is 4. 4/10 is 0.4, plus 1 is 1.4. And then plus, and then f at 0 is 1. And again, this is all getting multiplied by the widths, of 2 here. 2.6 plus 1.4 is 4, plus 1 is 5, times 2 is 10. So this adds up to exactly 10. So the area under the curve, wherever the graph of this function looks like, right, some parabola, over the interval from -6 to 0 is, approximately 10 square units, using just those 3 rectangles. And again, they might have a nice little picture for us here. Yeah, here it is. So those 3 rectangles, we calculate the areas of have, 10 square units of area. Now, remember, it's on a decreasing curve. So you see how the right endpoint approximations, these right endpoint height rectangles underestimate the actual area under the curve when it's decreasing. And keep that in mind. All right, so this is pretty similar, but just, it's the same function, but over a different interval and with a different number of rectangles. All right, so let's keep the function up. So it's the same function as last time, right? F of x is 1/10 x squared plus 1. But now we're on the interval from -7 to 1 using n equals, 4 rectangles. And they want us to do left ends as well, right? So that's a little different. Left end points, right? It says you make a left endpoint approximation, or, write a left Riemann sum. So again, I'll think of the interval. We got from -7 to +1. We're breaking this into 4 pieces, right? So the width of each piece, this delta x, would be 1 minus -7. That's, 8. And I'm breaking this into 4 pieces. So once again, like the last example, the width of each should be 2. So we're going to have 4 equal pieces here. For first piece goes from -7 to -5 for a width of 2. Then from -5 to -3, -3 to -1, and -1 to +1. But now I'm plugging in the left end points, so these 4 here, and then getting the heights, and then adding up the rectangles. So this area under the curve be approximately, and every single one of these will have times 2 times the width, so I'll just factor that out right now. And then you just have, the width multiplied by the sum of all the heights, which will be the value of f at these left endpoints, the value of f at -7, plus the value of f at -5, plus the value of f at -3, plus the value of f at -1. All right, so let's get these. Now at -7, that'd be 4.9 plus 1, that'd be 5.9. At -5, 2.5 plus 1, 3.5. At -3, it'd be 0.9 plus 1, so 1.9. And then at -1, be 0.1 plus 1, 1.1. Adding these up, these add up to 3. These add up to 9.4. So overall, this is 12.4, but then times 2, the 24.8. Honestly, I'm just going to put that and see if it takes it. I know it said enter as a fraction. No, it just said it all they want. No, this is just an example of what they mean by enter an exact value. So if I put in 24.8, that is an exact value here. So this area should be approximately 24.8 square units. Great. And again, they'll show us a nice picture. So you see over the interval from -7 to 1. Now, a lot of this is decreasing. Not all of it, right? This part from 0 to 1 here is actually increasing, but we still, because of the width of the interval here, we still tend to look again on the decreasing part, right? All the decreasing parts of this curve, plugging in the left endpoints and making these rectangles overestimates the area. Right, so the actual area would be something under 24.8 square units, but still, we're just estimating. All right, so this one's do it kind of eyeballing things here, right? This function doesn't have some specific equation to it. All right, so this is using left endpoints for rectangles. So the width of -2 to 6, again, that's 8 units. If I divide it by 4, that's 8 divided by 4 is 2. So our pieces would go from -2 to 0, 0 to 2, 2 to 4, and 4 to 6. And then I plug in the left endpoints, so -2, and 0, and 2, and 4, and get those heights. And then the area of the rectangles will be the sum of all the heights times the widths, times 2. The value of f at -2 is 5, plus at 0 is 4, 5 plus 4 is 9. Then at 2 is 5 again, that's 14 total for the heights now, and then at 4 is 3. So we get 14 plus 3, that's 17 times 2, right? The width for all of them is 34. The area of all these rectangles would be 34 square units. All right, again, they'll show a picture. All right. Here's when we're moving stuff. Let's see, they want right endpoint approximations now. So just make sure those right endpoints are on the curve, -6 to -2 using 6 rectangles. So -6 to -2 using 6 rectangles, n equals 6. And then make sure all these right endpoints, these black points here, give me the height to the curve. Try to have these black points be as close to being on the blue curve, it's a little too high, on the curve as possible. And those look pretty good, and that should be a decent estimate for the area under the curve using 6 rectangles and right endpoints there. Okay. All right, so this one asks us for midpoints. That's a little different because it's, x squared over 4, interval from -6 to -2. And, we're plugging in the midpoints, so not the left end or right end, but the middle value of each interval to get the heights. Write this one up. So this time the function is 1/4 x squared plus 1 around the interval from -6 to -2. And they want us to use just 2 rectangles and midpoints to get the heights. So again, if I break up -6 and -2, two pieces, the delta x, the width of each piece, that's 2 again. It's not always 2. I hope you understand that, right? It just so happens that the width of all these rectangles is 2 in most of these examples. It's not always going to be 2. Right? You saw that in some of those pictures with the movable points, right? The delta x wasn't 2 in those. Now we're plugging in the midpoints. So in this first piece from -6 to 4, I would plug in -5 to get the height. And then for the second piece from -4 to -2 here, I would plug in -3, right? These are the midpoints of these intervals. So the area under the curve would be approximately, the value of f at -5 plus the value of f at -3. And each of these was going to be multiplied by the width. So that quantity, the sum of those heights times 2. Now at -5, so that's 25 divided by 4. So that's 6.25 plus 1 is 7.25 plus, and then the value of f at -3, that's 9 divided by 4, which is 2.25 plus 1, so 3.25. And then this is all, after you add them, multiply by 2. This is 10.5, but then times 2 would be 21. Right? So 21 square units is approximating the area that they're asking for here. Again, they should have a nice little picture where they're plugging in, see the midpoint values. So you really can't tell if it's underestimating or overestimating at times. It underestimates from -6 to 5, but then it overestimates from -5 to -4, Here it totally underestimates, here it overestimates, so it's like you can't tell if it I mean, you'd have to refine it, make more rectangles and get a finer and finer approximation to get a better idea as to the actual area, but still it's a reasonable initial estimate. So this one I'll probably just say out loud. Then we're using, not really. No, the midpoints won't be so nice. I should write this one out. Yeah, the midpoints won't be best. There'll be some fractions here, or decimals. So this time the function 1/2 x squared plus 2. We're on the interval from -4 to 2. They're asking us to use 6 rectangles, break this into 6 pieces using midpoints again. All right, so think of the interval. And we're going from -4 to +2. So the width of each piece is going to be, this is 6 units. We're breaking it up into 6 pieces. Here, finally. The delta x is not 2, it's 1. So first piece would go from -4 to -3, then to -2, then to -1, then to 0, then to 1, into 2. There's your 6 pieces, 6 equal pieces. I know they don't look equal with my drawing, but they should be. They're asking us to plug in the mid, so this is the width of all of them. So the midpoints are all these in between, right? So negative 3.5, negative 2.5, negative 1.5, negative 0.5, 0.5, and 1.5, right? So those are all the midpoints. So the area under the curve will be approximately the sum of the function, all the heights at these values. So f at negative 3.5 plus f at negative 2.5 Okay, I'm just trying to think if there's a quicker way to do this, but keep writing it out. F at negative 1.5 plus f at negative 0.5 plus f at 1.5, right? These 6 inputs. Oh, I missed one. Positive 0.5 and then f at 1.5. Yeah, these 6 inputs, to all that, times 1. So I don't really need to write times 1. Okay. Now, I probably would go to a calculator. Let's see. So again, this is negative 7 halves. So that'll be 49 fourths, but then times a half. So 49 eighths. Yeah, it's not impossible, but I don't really feel like doing all that. So I'm gonna go to a calculator. So our function was, so I'll call it f of x like they did, was half x squared plus 2. And then we're adding up. Now every single one of these looks the same. So got 6 of these things. Start with 0, n equals 0, go to n equals 5. That'd be a total of 6 terms. And then every single one of these is f of negative 3.5 plus n, right? Because like when n equals 0, it would be f at negative 3.5, and then it just kept getting added by 1, right? So then when n equals 1, it's negative 2.5. When n equals 2, it's negative 1.5, then negative 0.5, then 0.5, then 1.5 when n equals 5. So this would be the sum that I actually put on my paper. So this ends up being 23 3/4, 23.75 for the area of all those rectangles. Great. And again, they probably give you some nice little picture like that with the 6 rectangles and all the midpoints plugged in for the heights. All right, so back to upper or lower sum. So here we're asked to find the lower sum this time. So remember, lower sum meant over each interval. You're plugging in the value that gives you the lowest height. So that way you're always underestimating the area. So as a quadratic from negative 4 to 0, this would be a parabola opening up. The vertex would be at 0, 4. So, from negative 4 to 0, if it's opening up, this would be to the left of 0, to the left of the center, the left of the axis of symmetry. So it'd be decreasing, be a decreasing function over this interval. So the highest point will always be at the left end. So I break this into 2 pieces. Negative 4 to negative 2, negative 2 to 0. The delta x will be 2. And the value at the left end of each will be that'll be the highest point. Ooh, I want the lowest, so the lowest will be at the right end. All right, so I'm going to plug in the right ends. So look, if I actually draw this out, right, again, lower sum, we're looking for the lowest point on each interval. So here f of x is 1/4 times x squared plus 4 on the interval from -4 to 0. So again, here's what that would look like. I know I'm going to be able to draw it because it's a very simple, quadratic. So from -4 to 0, you got 0, 4 would be the vertex. And at -4, you'd have a value of 8. Right, 16 over 4 is 4, plus 4 is 8. So you'd be on this piece of the parabola. All right, it's a parabola opening up, and the vertex is at 0, 4. So this is the piece of curve you're on. You're trying to estimate the area under the curve to the x-axis. Now they only wanted 2 rectangles, right? So delta x, again, the width of each would be 4 divided by 2, which is 2. So each of these pieces has a width of 2, from -4 to -2, and -2 to 0. And then they want the lower sum. All right, they ask for the lower sum. So all that means is in each piece, I plug in the value that gives me the lowest height, the smallest rectangle. So in this first piece, I would plug in, see the lowest would be at the right end because it's decreasing. So there's my lower rectangle, lowest rectangle. And then same thing here, again, it's decreasing, so the lowest point is at this right end. So here's the rectangles that we got to add up for our lower sum. So this lower sum, this area here, when I plug in -2, -2, it's 5, right? It'd be 4 over 4, so 1 plus 4 is 5. So this would be a 2 by 5 rectangle. So this has an area of 10 plus, and then this is a 2 by 4, so 8. So 18 square units is my lower sum here. And that, again, very hopefully clearly from the picture, underestimates it. A lower sum should underestimate your actual area. So 18. And then they'll probably have a nice little picture again. Yeah. Kind of like what I drew. A little better though, of course. This is asking for the upper sum. And this is another one of them cubics with a negative lead coefficient, right? -1/20 x cubed plus 1. So like an example we saw earlier, right? The derivative will always be non-positive, right? So this is going to be a non-increasing function. It's always going down, always decreasing. So the highest point in any interval we get for the upper sum will be at the left end. Remember, with decreasing, highest points on the left end. And if I use 3 rectangles here, I'll just be doing the left endpoint approximation. That'll give me the upper sum. So I'll go to paper. I got some room on this page. Let's just go down here. So the function this time, 1 minus 1/20th x cubed. We're on the interval from -4 to 2. So again, I said this is decreasing, right? It should be going down all the time. So when they want the upper sum, I'm just looking for, oh, and they had said make 3 rectangles, right? So the width would be 6 over 3, a 2 width again. And then for the upper sum, I'm plugging in the left endpoints for this one because at the left end, that's where the function will be the highest over each of these pieces. And we'll get an overestimate of the actual area. So the upper sum, I know I wrote it over there, but will be equal to the value of f at -4. And this will all be times 2, so let's pull the 2 out, right? Times 2. plus, and then the value of f at -2, right? The next, piece, just keep adding 2 to the inputs for the widths, plus f at 0, and, all that times 2. Now at -4, right? So, hmm, well, that's not so bad. You got -4 cubed is, -64. So it'd be plus 64/20ths, which would be 32/10ths. So 1 plus 3.2 would be 4.2. Plus f at -2. -2 cubed is -8. This would be plus 8/20ths or 4/10ths, so 1.4. And then f at zeros is 1. So this is a 5.66.6, and then times 2 would be 12 plus 1.2, 13.2 square units for this upper sum. Again, that should overestimate the actual area. All right. Again, they have a nice picture probably. There it is. See all those overestimating rectangles. All right, and then so this is back to, like 2 earlier ones we've seen from this objective. You're given another quadratic that would be a parabola opening down. The axis of symmetry would be at x equals 4. This interval from 2 to 3 is to the left of that. So once again, it would be you're on the increasing part of it, right? It's increasing to the left of 4, but it would be decreasing to the right of 4. Now, if it's increasing, and we're looking at another left Riemann sum, once again, we'd underestimate the area with a left Riemann sum. So again, if it's increasing and you're plugging in left endpoints for the heights of the rectangles, you're going to underestimate, and you're plugging in right endpoints, you'll overestimate. If it's a decreasing part of the function, you plug in left endpoints, you'll overestimate, and you plug in right endpoints, you will underestimate. This is underestimate like the other two that we saw. And this is, well, this time though, it's a right Riemann sum. So look, another quadratic, parabola opening down, the axis of symmetry, the middle of it would be at x equals 6. All right, it'd be if you look at the derivative, right, -2x plus 12, that's equal to 0 at x equals 6. This interval is to the right of that. You're on the interval from 7 to 8. So it's a parabola opening down. You're to the right, you're on the right half of it. So that's the part where it's decreasing. So I said in the last problem, right? If you're on a decreasing part of the curve and you plug in right endpoints for the heights, you're going to be underestimating the area again, right? It would be if you're decreasing, that's when the left endpoints, the left Riemann sums will overestimate, but the right Riemann sums will underestimate on a decreasing part of the curve. All right, wonderful. Okay, so that's it for this preview of this assignment. And hopefully watching me go through these here, explain a few things here and there, will help you when you go over this assignment on your own. And thank you very much for watching.